right, good evening, everyone. Thank you, everyone, for grabbing their seats. For those of you that don't know me, my name is Tyler Southam. I'm the VGS chair this year. Before we begin, I'd like to start with the land acknowledgement. So the VGS recognizes that we are on the ancestral and unceded homelands of the Hunkaminam and Squamish-speaking peoples, and are grateful to be on the territory. As a quick reminder, we do have our symposium this year, and it's going to be on June 6th. The topic is on foundations. Abstract submissions are on now. We've received some, and we'd like to receive some more. So if you have any interesting projects with either novel or sort of traditional case studies, we'd love to see them. Another thing we're looking at these days is the next CGS conference in Vancouver. So that's going to be in 2028. And right now, really what we're looking for is an expression of interest for individuals who want to be part of the organizing committee. So if you do have any interest, feel free to reach out to myself. You should have my email. It's also on the website. We can do that. Lastly, before we get started, there is the spring short course on MSE walls and reinforced slopes by Ben and Dov Lishinsky. That's going to be February 7th. We do still have some space in that, so if you're interested, please sign up on our website. And without further ado, I'd like to invite Moon to introduce our speakers today.
Thanks, Tyler. So today I'll get started off with introducing our three speakers. Sheri Molnar, with Associate Professor with the University of Western Ontario, Jamal Assaf with WSP, and Alireza Javanbakht with Jacobs. So those of you who don't know who Sheri is an Associate Professor at the University of Western Ontario conducting earthquake hazard research focused on advancement of seismic site characterization and earthquake ground motion prediction, focused on using numerical wave propagation simulation to account for local seismic site effects in seismic hazard assessment and mapping. She's been involved with the design committees of the 2020 and 2025 Canadian Building Codes, former director of the Canadian Association of Earthquake Engineering, and former president of the ERI British Columbia Regional Chapter. So this will be a three-part presentation. I'll let them coordinate how they transition. And without further ado, I'd like to invite Sheri to the board. Yeah.
Well, thank you, and we're grateful for the opportunity to present today about the Metro Vancouver Seismic Microzonation Mapping Project. And I haven't done the work myself, and this is the first time I've been able to help get some of the team here and present it to you straight from their research and straight from their mouths, rather than me translating it poorly. So we're one of over 30 individuals who are involved in the project. And so you just get the three of us as representative of that today. And I'll push to the next. In that the project started in 2017 and it's now 2025. So it's been 7.5 years. And I came and gave a talk to the VGS near the end of 2018. So only 1.5 years into the project, I was telling you what great things we were going to do. And now here I am, 7.5 years later, telling you what we have been able to do. And we've just released 29 seismic microzonation maps for Western Metro Vancouver. In 2023, we were extended to project funding to finish all of Metro Vancouver by 2026. And so we talk about that as phase 1 and phase 2 of the project, which is mapped out on the screen. And we make seismic hazard maps, kind of like the federal government, except that we're region specific. So we pay attention to what the ground conditions are like in Metro Vancouver and how that can alter earthquake shaking. And so we go further than the building code. We don't just rely on VS30 as the one summed parameter for what's going on in the subsurface. We actually built a very detailed knowledge of the three-dimensional geodata under Metro Vancouver to create models and simulate what ground motions are like at the surface, to calculate earthquake shaking amplification and liquefaction and landslide hazards. So our project was focused on looking at what would happen to earthquake ground shaking as it gets altered, as it travels through the one-dimensional site effects or one-dimensional soil column. But also Metro Vancouver sits inside of the late Cretaceous Georgia sedimentary basin, and that will alter long wavelengths or long period ground motions. This is the only region-specific hazard map in Canada that includes basin effects. And then we also pushed, or were asked or tasked to look at landslide and liquefaction hazard potential as well, or secondary hazards from the shaking that will occur. Think that these are all very common metrics that are done in seismic microzonation or region-specific seismic hazards. Tsunami is not considered for Metro Vancouver. We're quite a distance away from the subduction zone, so not as high of a interest to have that as something involved in the project. And we don't look at topographic effects, which could alter earthquake shaking as well. But we're about 5 years out from including that in our three-dimensional numerical wave propagation simulations. I don't think this crowd needs justification why this should be done for Metro Vancouver. We're in the highest seismic risk city in Canada. As a seismologist, why are these maps not available before now? It's because we are in the most seismically complex part of the country. Montreal and Ottawa had these maps before us because they only have to consider one earthquake source. But in Metro Vancouver, we have 3 earthquake sources: in the crust, in the North American crust, in the subducting Juan-de-Fuca plate, and in the interface between them, the Cascadia subduction zone. So the probabilistic seismic hazard is complicated. We also have the most variable range in geology. You go from the ocean to 1,000 meters up in the North Shore Mountains. In Montreal, the sediments, post-glacial sediments, are about 30 meters thick, and you might have a couple meters of till. In Ottawa, you have the lowest velocity sediments in all of Canada. That's different. That's a challenge, but they can only be a maximum of about 100 meters. In Metro Vancouver, you have the Fraser River Delta, which is loose, young sands that can be up to 300 meters thick, and it can sit on glaciated sediments that are maybe up to 500 meters thick. We can have 800 meters to a kilometer till you hit rock. This is not seen elsewhere in the country to handle. This is why we have never had these maps produced before. And then the answer there is that we want to push to making hazard maps. We want to consider the earthquake shaking intensity and therefore what the amplification level will be, and will liquefaction and landslides be triggered. Knowing an update or as much improvement as we can get about the subsurface ground conditions and the latest knowledge in the seismic hazard or the seismic source model that comes from the Federal National Code, and merge these together to create level 3 or very high level, very intense, comprehensive, sophisticated analyses behind those mapped products. For geotech engineers, we need a geodatabase. I think you'd be interested in this. And so we tried to do this in a cost-effective way. First, obviously, there's been geodata collected for decades in Metro Vancouver, so we looked online, could see what we could find. And then we talked to engineering firms or agencies or organizations and got access to geotechnical reports and extracted that data. And eventually ended up with geodata that's available at 15,000 unique locations. Most of those, 90% of the data from proprietary reports is from invasive testing: boreholes, drill holes, CPT, SCPT, SPT. What we also paired that with was the project for this cost-effective approach. The government paid for us to come every summer and put seismometers on the ground and do non-invasive seismic testing. When we put one seismometer on the ground, we record 3 components of motion, and we can look at the amplitude difference between the horizontal component and the vertical component. The horizontal component will include surface wave and shear wave amplification, and we can tell how much more increase in the shaking intensity there is compared to the vertical component. In 30 minutes to 60 minutes, having a seismometer on the ground, we can tell how the ground is filtering particular periods and amplifying other periods, or what the site period is like for the site. We did that at 2,300 locations across Metro Vancouver, all the blue points. We then target open parks, schoolyards, where we can make arrays of these seismometers and track how fast a surface wave is traveling between them at different wavelengths, and therefore get a velocity structural picture of what the velocity structure is like under these locations. We did that over at 120 locations, or the black triangles. We did not focus on the Fraser River Delta. We knew what the velocity structure was, mostly from the GSC, having done a lot of drilling in the 1990s. Those are the softest sediments of most concern. We never knew, though, what the velocity or how stiff the glaciated uplands of Vancouver, Burnaby, and Surrey is. In geotechnical speak, you hit refusal. Done. Foundation can go up. Seismologists are not satisfied with that answer. We need to predict what earthquake shaking is as it travels through that relatively stiff ground. I can tell you that the glacial tills in Vancouver are about 400 meters per second in Rayleigh velocities. It's a little stiffer in Burnaby, and it's even stiffer in Surrey. That we did not know before. So in order to understand the stiffness or the velocity or the speed at which seismic energy is going to travel through the subsurface and the upper 1 kilometer, we needed all of this information together. You need good, detailed, high-resolution geotechnical testing. Every few centimeters, getting me a CPT cone tip resistance, great. But it's only for one little spot, one little drill hole. I can use a ray that can get me a volume of answer that helps me understand on average what the wave speeds are like at these locations. I needed both of these to make 3-dimensional models of the subsurface of Metro Vancouver. What we produced in a nutshell is that we were tasked with working on 3 seismic hazards. We create this geodatabase, which on paper said, we'll get all that data in the first 2 years from everybody, but of course, as you start these conversations, it takes about 5 years to get all the geodata. And then we can translate that geodatabase into easy metrics that are easily put on a map. So how thick is the softest stuff? A post-glacial sediment thickness map. What would I use this for in geotechnical practice? Well, now I know how deep my piles have to be. We also make a depth to rock map. We also translate into the most common seismic hazard site term, the time average shear wave velocity of the upper 30 meters, a VS30 map. That is what a seismic microzonation project would normally make, 1 VS30 map. We made 29 maps because we also consider what the earthquake shaking is like in Metro Vancouver from the 2020 building code, or the 6 Canadian seismic hazard model, and we propagate that through what we know about the subsurface conditions to create amplification shaking maps and landslide and liquefaction hazard potential maps. Quickly, hopefully, to talk about seismic microzonation maps in general, or give you some context. In the world, they make seismic microzonation maps. For example, in Italy, every city has to have one. We do not have these requirements in Canada currently. They are an expression of how the differences in how you would experience an earthquake is going to be different in different neighborhoods related to how the subsurface ground conditions has changed. Or we zone areas that would be similar because the underlying geophysics and the underlying geology is similar. And maps uniquely allow us to reach technical end users who understand seismic hazard, but I also have to get people to make decisions, say emergency managers or planners, land use planners, local governments in their community official plan updates have to try to use this information, and maps are helpful to get that conversation started. But for you, the data behind the maps, the fact that we know a lot more about the subsurface ground conditions in Metro Vancouver is the big thing that has happened. And maps are just an expression of that. In seismic microzonation mapping, internationally, they talk about it as levels. At the first level, you might download a remote sensing data set that you can get freely online. You could be a geography student and doing this as a homework assignment. That's level 1. there's high slopes. There's going to be landslide susceptibility. Level 1. Level 2, you start to get more and more data. And the more data you get, the higher the spatial resolution of your mapping can get. And then you might start to move to this level 3, or you might start to do a calculation as to will that slope actually fail given the earthquake's seismic intensity. And that's what we did in this project. We pushed to level 3, or we consider what the seismic shaking intensity is. And so it's taken us 7.5 years and quite a bit of money to do that. Last but not least is that these maps have been available in Canada since the 1990s. Most of them were for VS30 or seismic site class, or so going back to you only had one map made for the whole city. They have been accomplished for the highest seismic risk cities in Canada. A big problem is that they're just images or a PDF that you can download. You can't play with it. It's not in GIS form. And that is no longer acceptable. When we were doing engagement over the years, every time we want these maps in a digital form. We have released them in digital form. They also are level 3. I have no idea if they're going to be helpful. I don't know if it's too complex for engineers and decision makers to handle these types of maps. Maybe we should have stopped at level 2 and VS30, but we tried. And I'm hopeful in the next 10 years, I'm interested to see how successful it is to make an equal playing field in the access to site-specific seismic hazard. Think of it that way. We have calculated what ground shaking is like at many locations in Metro Vancouver, and normally you would have had to hire a geotech engineer to do that and perform the PSHA and do that site-specific analysis. We now have an equal playing field for the cities that they have an idea of what that answer is from these maps. So they should be asking you, like in these places, we should deviate from the code. We should get you to do site-specific analysis. Last but not least is that all these images are technically showing you the same metric, but obviously they're different colors. How can you interpret them readily, fast? You know, if seismic site class C was always green, we could all read these maps together immediately. We need these kind of standards. And so these are some hindrances to the comprehension and use of our maps that have been available since the 90s. A little piece of information is that NRCan has a seismic risk modeling team, and they're including VS30 in the next round of the National Seismic Risk Mapping. And so they're incorporating all of this good level 2 VS30 or seismic site class for these cities in Canada inside of the map moving forward. So rather than wait to the end, let me tell you the coolest things we did or the greatest things that are coming out of the project. We pushed to level 3, like I said. That's rare or never been done before. We need uptake. So we had a technical peer review committee assembled with structural and geotech engineers from Engineers and Geoscientists of BC, and they helped create a new professional practice standard for development and use of seismic microzonation maps in BC. That's a great step forward towards national standard. And then we didn't wait till the end of the project to say, ta-da, here's maps, hope you find them useful. We talked to people about what we were making and had conversations about how that was being displayed so that it wasn't going to be too jarring when we made it available to people in the end. So just selling it that it's now available online to have access to these professional practice guidelines for making seismic microzonation maps in British Columbia. EMCR, our provincial funding, may not be paying for this for every community in all of British Columbia in future. The geotechnical engineers in the region may be asked to create seismic microzonation maps for other cities in British Columbia in future. And we hope you know about this standard that you should be aiming for these maps in BC. From the invasive data in the Geodatabase, we were able to develop brand new region-specific relationships to relate shear wave velocity to CPT or SPT. We were able to understand what the average cohesion or friction angle was for particular slopes. And so and then with our non-invasive data set, we really pushed or made it very good to know what the velocity was like in the sediments in any kind of sediment, not just soft stuff, and at great depth, so that we could create a 3D model from which to then very quickly calculate what the average velocity is and what site period is. And obviously we would look at earthquake data when we could to validate our work, and we looked at other sites in the world that had experienced nonlinear site response that were similar to sites in Metro Vancouver to calibrate what our numerical models were producing. A little more of the exact same story, but in graphical form. We updated and have greater coverage knowledge in VS30 and the depth of glacial sediments or the thickness of soft sediments. And we also never knew what the velocity structure was like in glacial sediments until now. And we didn't have a very good picture of what the predominant period of the ground or how the ground is filtering earthquake energy before we had all these site period measurements. And of course, the key output is that we've created these new 29 region-specific seismic hazard maps. Again, 11 of them, or a group of them, are only this level 2, only the susceptibility level, or has no idea about the intensity of seismic shaking. But they tell us, they try to convey to you the new knowledge, the new resolution that we have of what's going on in the subsurface ground conditions in Metro Vancouver. So these are going to identify where natural ground is susceptible to changes in earthquake shaking, liquefaction, or landsliding. But does it actually trigger liquefaction or landsliding? Or how is the ground going to be altered in terms of increased earthquake shaking or amplification pushes us to that level 3? And now I'll transition over to Jamal Assaf, who led doing the seismic shaking amplification mapping for our project.
Thank you, Sheri. And of course, I would like to acknowledge also the efforts and all the participation from all the colleagues that contributed to this work. And I'm going to be talking about the shaking hazard mapping. And we produced 21 maps. 8 of them are susceptibility maps, and then the rest are actually hazard maps. And those maps include the 1D site effects and 3D sedimentary basin effects. So if we start to talk about the susceptibility maps, or what we can call as site amplification predictors, we can talk about the quaternary geology, which most of you are familiar with, and then we created other important maps, such as the depth to firm ground, or depth to till, we call it. In this map, it's called post-glacial thickness. And then we have the VS30 map and the site period map. And one interesting thing here in Vancouver is there's no one single parameter that can describe your actual site response. So if I give an example here in Surrey and Vancouver, you have the same VS30. I don't know if the mouse is showing, but Surrey and Vancouver have the same VS30, but if you see, the site period is very different. It's short in Vancouver and long in Surrey. If we take another example in Fraser River Delta, where we have the same VS30, we could have very different depth to till. In some places it's 30, in some places it's 300. So those two locations will give very different response. And this is important to keep in mind. Now, in terms of how did we develop these maps, and as most of you know, we don't have enough earthquake data to come up with regional amplification maps. So we had to go back to numerical simulations, or what we know as site response analysis. So we selected 55 sites to basically sample the subsurface conditions in the region, as complex as we saw in the maps. We developed the 1D columns based on existing data. We used input time histories, just typical site response analysis, and we came up with amplification functions that we will map out into different zones. And in terms of the time history scaling, As most of you know, selecting the reference site condition for site response is a very important piece of information. And as you know, we have two different types of rocks. We have the tertiary young rocks in the lower mainland, and we have the pre-tertiary rocks in the North Shore. So it was very challenging to select a single reference condition for the whole region. So we ended up using 760, VS30 of 760 for the lower mainland and 1500 for the North Shore to account for the stiffer rock. And then we used the 6th generation seismic hazard model to develop the target spectra using the individual UHS of earthquakes for 2% and 10% in 50 years. These are the probability of exceedance that we typically use in engineering design. And then we scaled 11 time histories for each type of earthquake and each return period. So 3 types of earthquakes times 11 times 2 return period, we end up with 66 time histories for each site. And we do simple scaling up and down for sites that are close to these reference sites that we develop the time histories for, and then we can map them out for different sites across the region. So we use 3 sites, we develop time histories, we scale them up and down to have 66 time histories at each of the 55 sites that we selected for site response. And then we, for the site response, we use deep soil. We use the MKZ model to fit the modulus reduction and damping curves, and we used the modulus reduction and damping curves that you see, and those are mainly recommended in the 2007 Task Force Liquefaction report and typically used in engineering. These are 3 examples for sites in Vancouver, in the North Shore, and in Fraser River Delta. And as you can see, we have very different ground conditions in these locations. So what's the next step in terms of, we have 55 sites, we calculated 55 amplification functions, and then how do we put them on a map? And we thought that we could bin the results into different bins based on VS30, the site period, and the depth to post-glacial sediments, as you see in the bottom left. So what we did is we classified those 55 amplification functions into 14 different classes based on these 3 criteria. And the reason is we can't describe site amplification based on one parameter. We actually needed all 3 to have 14 different zones that have different site response during earthquake. And after we classified them, we used those maps that we have available to map out the amplification values. And how do these amplification values look like? These 14 classes, we start from, we start from site class A in the top, which is the stiffest, and we go down to site class F. Now, as I said, VS30 is not enough, so we used site period as well to differentiate site classes C and D, because those were the most variable. And as well, we used the HPG, or the depth to till, to basically come up with these classes. And we start from the top left, where we have the stiffest sites, and we can see amplification at shorter periods in zones C1 to C3. And then as you go towards softer sites in the Fraser River Delta, you can see the amplification starts shifting towards longer periods. Now, this is good in terms of 1D site effects, but we also know that Metro Vancouver has basin amplification. And before I go into basin amplification, maybe it would be good to show some trends that we could see. So the darker colors are actually where you see more amplification, and then we can see for stiffer sites we have more amplification at shorter periods, while at softer sites in the Fraser River Delta you can see the de-amplification for stronger shaking. In terms of the longer periods, you can see there's not much difference, but you see that the amplification is mainly happening at longer periods where your site is actually deep and soft. In terms of the basin effects, the same approach. We don't have earthquake data to use it, so we go back to 3D simulations. And the way 3D simulations work is you start by modeling the source, the rupture at the source, and you carry out these waves using massive 3D velocity models from all the way from the source to your site. And these models could be up to a few hundred kilometers wide. We used for the three different earthquake sources more than 40 scenarios of earthquake and 6,000 locations in Metro Vancouver to come up with those amplification for basin effects. And the way the basin amplification was derived is we used the simulation at the surface, and the simulation includes the path, the source, and the site effects. So we have to remove the source and the path, and that's what you see here at the top row. And then next we need to map out this basin amplification. So we have to use a certain metric, which is typically the depth to 2.5 kilometers per second for shear wave velocity, and that's what's basically in the second row. And in the third row, this is what we're doing to correct for shallow site effects. This basin amplification, or this term, has both shallow and basin amplification, so we need to remove the shallow site amplification so we can add the net basin effects to an existing shallow site amplification. And then we can basically multiply the basin amplification by the 1D site amplification that we came up with. And this is how the basin amplification looks like at 2 seconds and 5 seconds. You can see at the deepest areas in Fraser River Delta, you see the highest shaking. And as you go to the north, you have less and less amplifications from the basin. So we came up with basin effects. We came up with 1D site effects. We multiply both, and we can come up with basically final shaking or amplification, de-amplification map where we have both components here. And as you can see here, we have similar trends where we have amplification at shorter periods and then de-amplification with stronger shaking. However, at longer periods, you can see those are not affected much by nonlinearity. So the overall methodology, we used 1D site effects, 1D site response. We used the available maps and added basin amplification to finally come up with maps that include 1D and 3D basin effects. So this is common. How different are these values from code values? And it's complex. The first is the code values basically do not include any basin effects, at least from the Georgia basin. So we know that these maps do include this basin effect. The second one is the site effects in the code are mainly derived from different regions in the world and not necessarily applicable to our region. The site amplification is oversimplified in terms of modeling. The code only uses VS30, which we already know is not enough. And some ground motion models also lack nonlinear site effects, so they don't change with the increased intensity. So in general, those maps, we're including more site-specific information to develop the site amplification factors, and they represent the best knowledge we have for the seismic hazard, which we can use in planning and mitigation and risk reduction. And this is just an example how they compare to the code. Just to give an idea how those values are, you can see the code values in red. So at shorter periods and stiffer sites, we're above the code. At deep sites, we're generally below the code. And that's how we can see it on a map. The darker colors means we're above the code, and then yellow colors are we're under the code. So basically for stiffer sites, we're above, and deeper sites, we're below the code. And I think with this, I'll invite Alireza to talk about the liquefaction hazard mapping.
Thank you, Sheri and Jamal, for the presentation. So I'm going through 3 levels of liquefaction hazard mapping. So we have level 1 and level 2 of liquefaction susceptibility mapping, that it only considers whether the ground condition is susceptible to liquefaction without considering any earthquake threshold in generating these maps. So the first level would be the liquefaction susceptibility map based on only qualitative approach. So we can use the map of surfacial geology map, that surfacial geology map that you can see it here, developed in our project map number 1. And also we use map number 2 for the groundwater level developed within Metro Vancouver region. Then we consider some qualitative factors to rank the liquefaction susceptibility, such as geologic age, depositional environment, and material type. If we do that, then we can do the liquefaction susceptibility ranking for every geology unit that we have in our study area. For example, we did that for NGANF, the first geology unit that you see it here on the map. And you see the age is less than 500 years, so it's a very recent deposit. And also it's mostly sand, so we can expect to see a very high liquefaction susceptibility ranking for this geology unit. But we also had the advantage of having some in situ measurements within some geology units like CPT and SPT informations. So we use those information to calculate the thickness of liquefiable layers over the depths of 20 meters. And then also we calculate the average of CRR. So if we combine these data with qualitative approach that we have, then we can advance to level 2 of liquefaction susceptibility mapping. So by using this data, we can confirm our initial guess, or we can readjust our initial guess. For example, for the unit that I already talked about it, we have around 54 in situ measurements. And our calculation shows the average thickness of liquefiable layer is around 13 meters. So we are dealing with the conditions of thick liquefiable layers. So these thick liquefiable layers can confirm our initial guess for very high of liquefaction susceptibility ranking. If we do that for our geology unit, we can make level 2 liquefaction susceptibility mapping that it's only based on the soil condition and groundwater condition and the qualitative factors that I already mentioned. So we do not account for any earthquake scenarios or any earthquake threshold in generating level 2 of liquefaction susceptibility mapping. The map is already available. You can go to our website, check the map, explore different areas. And as we expected in most areas in Richmond and Delta, we have high and very high liquefaction susceptibility ranking, while in areas like Burnaby, Vancouver, or most areas in North Vancouver and West Vancouver, we have low and very low liquefaction susceptibility ranking. In contrast to level 1 and level 2 of liquefaction susceptibility mapping, we have level 3 of the mapping, which we account for the earthquake scenarios to generate the liquefaction hazard map. What happens when the strong or very strong ground motion affects the Metro Vancouver region? So we consider 2 specific return periods of 475 and 475 years to construct the liquefaction hazard map for the region. But before generating the map, we need to have a metric to predict the liquefaction damages at the ground surface. So these are 3 famous liquefaction manifestation models that could be used for generating liquefaction hazard mapping. The first one is LPI, which calculates the liquefaction potential for the whole 20 meter depths of the soil column. We come up with a single number. Let's say your LPI is between 5 and 15. We categorize the hazard as high. We also have LPI ISH, which is similar to LPI, but it has a difference of considering the effect of non-liquefiable layer in the calculation of LPI ISH. So we expect to have lower values from LPI ISH compared to LPI. We also have LSN, liquefaction severity number. The description from LSN matches with the description that we expect from settlements from liquefaction, because as you see in the formula, we have the volumetric strain. But we have one limitation for using LSN, because in some areas we only have VS profiles, and as we know, we cannot do the volumetric strain calculation for VS profiles. So we decided to go for LPI ISH to generate the liquefaction hazard map. So we incorporated the LPI ISH in the performance-based earthquake engineering framework, PB framework, that you can see it here. And we obtained the mean annual rate of each earthquake scenarios from 6 generation ground motions, and then multiply that by the distribution of LPI ISH for each earthquake scenario, and then do that for all earthquake scenarios. And finally, we can construct the LPI ISH hazard curve. By doing this, we are not limiting ourselves to one earthquake scenario or one single return period. We are considering all earthquake scenarios in the calculations in LPI ISH calculation, and from this curve we can derive the LPI ISH for the targeted design level. For our project, the targeted design level were 475 years and 2475 years. So we did that, our Python code did that for over 1000 CPT and VS profiles, and we could develop the first probabilistic liquefaction hazard mapping for Metro Vancouver region with LPI ISH, as you can see on the right side. In addition, we developed some additional maps that could be useful for soil improvement application. We developed the map of thickness of liquefiable layer only from CPT data. We determine the thickness of liquefiable layer, and you can see the distribution of them. We also developed the map of return period of liquefaction, which shows for our region the return period is changing between less than 100 years to 500 years on average. We also developed the probabilistic factor of safety hazard map, which has the similar concept with LPI ISH. So this time we incorporated factor of safety in PBE framework, and we could construct the FSL hazard curve and then generate the map. And the last map that we generated was delta QREC map, which would be useful for soil improvement application. Delta QREC means how much soil densification is needed or is required to prevent liquefaction. The more negative values of delta QREC or more reddish color that you see on the map, it means that we need to do more soil improvement to prevent liquefaction initiations. So the map level 2 and level 3 for strong shaking and very, very strong shaking are now available. You can go to our website and explore the map. But for the last thing I should say, but remember that these maps can be used only for preliminary estimation, and they are not the replacement for site-specific analysis. Thank you. Over to you, Sheri.
Okay, so how can you get your hands on these maps or the data? We have published the maps as a typical traditional map that you would put up on the wall. It's a poster-sized PDF. you could zoom in on the computer screen, or you could also download the GIS file that's available as well. This is a Borealis open data repository. Borealis is a Canadian data repository, which was important to us. And then this is the permanent place for these files. Even if our government partner changes their website, you will always be able to get these files. And last thing to say is that the map sheet and the legends and the colors is part of this standardization or through consultation over several years, how people wanted to have the explanation of what's being displayed. Our project website also now has an open data portal under our products webpage. On there you have 3 options, number 1, number 2, number 3. Of course, I go out of order. Number 2 is that you would go and get to that link to these published maps, which is what I was just showing you as the Borealis site. So if you press number 2, it'll take you to that open data repository on Borealis. We also, in number 1, spent about a year and a half working with Western Map libraries to create an online environment to look at these ArcGIS layers. And so you can click on any map option on the left and you'll get some explanation about and description and potential uses about the map on the right. But you can also zoom in, you could turn layers on or off, and you can click anywhere on the map and get a value. You don't even have to download it. You can decide whether you want to download it by playing with it this way. Our government partner is doing the same to create an online environment for probably local governments and First Nation communities to access these maps. There is discussion about what kind of level of detail would be available to making them public. And so in conclusion, we've made about 11 level 2 susceptibility maps, things like liquefaction susceptibility or VS30. But these maps are only trying to communicate to you what the new knowledge we have about subsurface ground conditions in Metro Vancouver. There was never a regional geodatabase available for the whole comprehensive Metro Vancouver region before now, and that these maps are relatively usable for decades until such time that the geology changes significantly or that there's more data available. These maps can be used. But they don't consider what the seismic shaking is. And we therefore went to level 3 and made maps that are in consideration of whether or not what the seismic intensity shaking would be, and therefore where will earthquake shaking amplification occur and how much or what's that factor change, as well as where and the inferred severity for liquefaction and landslide triggering. So these maps do consider the regional seismicity, and they're made for 2 different input shaking intensities. And do I regret doing that? Do I regret making the double amount of maps? No, not yet. The whole purpose was to make sure you had 2 maps in front of you that says, okay, you can design according to the code or like for very rare 475-year return period. But you're much more likely to experience the lower return period type shaking more frequently. And it's up to you what level you want to design for. Or also, you can see that our liquefaction maps, even for 475-year return period, we expect relatively quite amount of liquefaction, even happening from strong shaking in Metro Vancouver. But for landslides, we don't see that a lot of landslides are being triggered at that strong shaking level. It's going to take a very strong shaking level or a 24-75-year return period. So it's kind of interesting to have the 2 versions of maps. And so finally, maybe you understand this graphic and appreciate these layers of differences, or that there's 29 maps. And then lastly is that the project's not over. We're continuing into 2026 to create similar maps for the most eastern communities in Metro Vancouver. So there were 8 of us out here last summer performing seismic testing at 42 locations in detail and 433 locations with a single seismometer. And we'll be back this summer, and if you have any desire to ask questions long past our time together today, my email is there, And I'll thank Jamal and Alireza for presenting to me today. Thank you.
Thank you all. Do we have any questions? All right, Carrie.
I noticed on the maps that you've excluded a lot of the First Nation lands. Why?
We were asked to remove the data and mapping within First Nations communities for those that are being made available online. But each First Nation community gets their own version that has Metro Vancouver and their community included. Yeah.
Any other questions?
I saw when you did your ground motion selection that you would match to the entire period range. I think 0
Correct.
to 2 seconds.
To 6 seconds.
6 seconds. Just wondering if you kind of considered just matching around the site period, because you knew the site period of each location. Did you guys consider kind of constraining
Correct.
that matching?
We actually had to select something to apply regionally, so it would be a lot more comprehensive when we do 55 sites if we have different ground motions for each site. So that's why we selected a wide period range, so we can cover all the periods that are in the sites, right? Because we have very shallow sites where you have site period less than 0.1 seconds, and you have site period more than 4 seconds enrichment. So we wanted something to be covering the whole range.
Any other questions?
So based on the field information collected, have you come across data that is either conflicting with each other, or did you get to choose which one would be more reliable and kind of tend to provide more of that information?
Now you're chipping away. That's a great question. So things we don't tell you. Let's say I sold you on the fact that we put down a seismometer for 60 minutes and get site periods. We don't see that the site period should be as long as we anticipate from calculation in our 3D model. So our site period map says that the periods could be as long as 4 or 5 seconds in the deepest part of the Fraser River Delta. But we only ever measure with our seismometer on the surface that it's about 3-ish seconds. At some point, the MHVSR doesn't see how deep it gets. So our post-glacial sediment thickness maps and our total sediment thickness maps are this interesting merger of invasive data, where you actually hit something and we know it's that horizon surface, and geophysics, where it got stiff enough. So we don't say it in bright lights, but our post-glacial thickness map is almost like what's the depth to a VS of about 400 meters per second. Those two are correlated. And in the total thickness map, the correlation seems to be when you get to 800 meters per second, it seems to be depth to rock. These are what we correlate, or these are the two metrics that have gone into the map to create the same horizon. There's a geologist who would make create what the depth to rock is, and then there's a seismic person or a geophysicist using the seismic data, and we had to merge these together.
All right. Well, if there are no other questions, that's been a small token of appreciation, and thanks to our speakers.
Thank you, Sheri, Jamal, and Alireza for presenting today. Since Sheri's flying off, we're giving her an assignment. And between Jamal and Alireza, I think you guys can exchange if you guys prefer. But thank you again for presenting. It was a great presentation.
Thank you.
Everyone, I would hope enjoyed, and this will also be posted on our website.